Did you see the Did you see the flooding right outside the library?
No, I didn't.
See?
Is there a lake? Lake Fullerton?
Yeah. Like the benches.
Oh my goodness.
You're gonna go swimming in there, man.
Oh my God. Yeah, I don't know why they had us come today.
I know. I
Wait.
feel like today was worse than
Yeah.
yesterday. I don't know, man.
I think just whoever's in charge of like emailing everyone, just like I just like changing stuff. It's like let's email everyone 4:00 p.m. Don't come to school tomorrow. Oh, come to school tomorrow. And so
I was kind of like expecting an email all the way out here.
yeah,
But never happened.
yeah. They just like fucking with us. That's what it is.
Dude, it's just like 6 stories tall. It's yesterday would have been better to go in the event because there was less flooding. Today it's been like a full day of rain. And actually it's flooded out. So now it's just like, why bother?
I was hydroplaning so much on the freeway this morning. It's scary.
I'm glad I'm going in. Had some guy trying to go like 85 past me. I'm like, dude, you're gonna get in an accident. I don't know what you expect of me, man.
Yeah.
I know people. Well, I knew people. I don't know if they. Question. Do you have the option saying that I don't want to go in today? We'll do it online.
Yeah. So each semester they give us 6 lectures of like sick days where you can work online. Yeah. So I might be sick sometimes this semester, but but I couldn't teach. I wasn't ready to teach from home today because I leave my iPad in my office. So I'm like I had to come here to get my iPad anyway. So exactly.
I'm gonna give up, man. And she didn't. There was only. I don't know. I feel like showing up to his lectures is trivial. Going. Wait, they're supposed to be signing that for figure out what's that. I can be number 2. I have no idea. It's not like halfway done. So yeah, so I'll already just sitting there and go to the 10 minutes. We were in practice. Yeah, I know that. All the way to the nonsense, all the way. I was just like cuddling into it. It was fun. You know the which one button it is? You can't go to phone. No, I didn't. Just sitting there in trouble. Oh, yeah, then you done it. They said she was German Shepherd, but she looks like one page sister. I don't know why. I was thinking about taking more pictures. Just put once.
All right, it's 1 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today? Staying dry, hopefully. Hopefully everyone's Zoom staying dry too. It's really raining out there a lot, in case you haven't seen. So thank you guys for making it out today. Okay, so the plan for today, we're just going to continue where we left off. So we left off last week talking about arithmetic gradients. So we'll finish up talking about that. I have one example to do for that, and then we'll go and move on to the next things, which is the compound interest tables, and our first big unit, which is on present worth analysis. Okay. All right, so I guess just one announcement I have is just homework problem set 1 is out there. So make sure you guys are working on that. So you guys should have everything you need to finish up that problem set. I believe it's due this Friday or this Sunday. So make sure you guys finish that up. If you have any questions on it, definitely come by office hours. So I have office hours today, right after the lecture, and then Thursday, right after the lecture. Or you can always email me, and I can answer your questions through email as well. Okay. All right. Any questions I can answer before we get started for today? Everyone have a good weekend, despite it being all wet. So I went to a show this weekend. It was called Trilogy and at SoFi Stadium. So it's a concert for an artist or a DJ, I guess, named Millennium. My wife is a lot more into it than I am, but she's been wanting to go to one of these things with me for a really long time. So I went with her, and a couple of my really good buddies came too, and it was really nice. And so as you get older, it's really hard to find time to do these kinds of things and have these kinds of experiences with the people you love, just as people start having kids. People are having kids my age, getting busy with work and family stuff. And so it was a really good weekend. I was really glad to experience that with my good friends. So yeah, there might have been some other things that kind of made me feel more sentimental than usual that I was doing that night. But yeah, it's a great experience. But definitely, hug your friends, tell them that you appreciate them. I think people always kind of shy away from that because they think it's weird, but it's it's always well appreciated. So definitely take care of your loved ones. Okay, so let's go ahead and get started. So where we left off last week was a concept called arithmetic gradients. Okay. So arithmetic gradients are our last form of cash flow. And so if you recall from last week or last Thursday, we were talking about 3 main forms of cash flow that we can convert between, right? So we have present sums, which are a single lump sum of money in the present day. We have future sums, which are just a single lump sum of money that take place sometime in the future. And then last Thursday, we spent most of the time talking about uniform series, which is a recurring type of cash flow. Okay. Arithmetic gradients is another recurring type of cash flow. The difference between arithmetic gradients and uniform series is that arithmetic gradients increase in value over time. Okay. And so if we were to draw it out on a cash flow diagram, okay, it would look something like this. Notice how I'm starting in year 2. That's going to be pretty significant. Where this amount here is G, 2G, 3G, 4G, and 5G. Okay. And so each subsequent time period that you have for the gradient, it's the value is going to increase by the amount G. Okay. All right. Okay. And so that G is typically what we want to solve for in each time period. Okay. All right. So the last thing that we did on Thursday was I gave you the formulas for converting between arithmetic gradients and the other types of cash flows. Okay. So let me just write these down again one more time for you. Okay. So first we have an F and G conversion. So if we're converting between a future sum and an arithmetic gradient, it would look like the following. So we have F is equal to G divided by I, multiplied by quantity, 1 plus I raised to the n minus 1, all divided by I, all minus n. Okay. We have the P and G equation. So we have P is equal to G multiplied by quantity, 1 plus I to the n minus I n minus 1, all divided by I squared, 1 plus I to the n. Okay. And then finally, we have the A and G equation. Okay. And so remember, I'm only giving you these equations in one way. And so this is, these are equations where if you're given G and you need to transform it into either an F, a P, or an A, but you can always reverse these equations as well, right? And so you can just use just simple algebra. So let's say that you're given a present sum P, and you need to convert it to a G. Okay, you can still use this equation here. Okay, you can just rearrange it so that G is kind of located on the left-hand side of the equal sign as opposed to on the right. Okay. So all these equations are reversible. You can use them in the other way. All right, so we have A and G. So A is equal to G times quantity, 1 plus I to the n minus I n minus 1, all divided by I, 1 plus I to the n minus I. Okay. So these equations here are a little bit more complicated, so they're a little bit more scary looking, but they involve basically the same variables. And so the only besides the cash flow type, besides the G, the only other variables you need are just the interest rate, I in decimal form, and the number of time periods n. Okay, it's just kind of different variations of that. So they look more intimidating, but not as bad. Okay, and so in the example that we're going to do, we're going to use one of these equations. But it'll be kind of just like the same things. Okay. All right, so that's basically where we left off last time. We're just kind of introducing this concept of the gradient, and then showing you how to convert between the different ones. Any questions on any of this? All right, because I know we kind of left it off pretty quick last time. So okay. All right, so before we do an example with the arithmetic gradient, I did want to cover the standard form for the arithmetic gradient. So if you recall from last Thursday, we spent a lot of time talking about, if you have situations where you have different types of cash flow, or in different types of cash flow in non-standard form, oftentimes you have to perform multiple conversions in order to get to the right form. Okay, so the same thing can be applied to G. But the tricky thing with G is that its standard form is a little bit strange. Okay, so the standard form for G, probably the most tricky part is that it kind of really starts in year 2, okay, or time period 2. Keep saying year, but it should be time period. Okay. And so if you look back up at the cash flow diagram that I drew up here, right? The only time that you start seeing G is on time period 2. Okay. So you don't have any cash flow on time 0, right? So the only thing that occurs on time 0 are present sums. Okay. And so time 0 is already kind of, it's time 0 is reserved for present sums. And so if you remember from uniform series, the uniform series didn't have anything on time 0 either. Okay. So the question I get a lot is why doesn't the standard form for the arithmetic gradient have anything on time period 1, right? So that's kind of the big difference between the arithmetic gradient and the uniform series. So uniform series does have something on 1, okay? Turns out it is there, it's just not visible, right? And so if you look at this diagram here, we're starting counting at time period 2, and we have an amount G, okay? And each time period after that, we increase by G. What you have on time period 1 is actually 0G, okay? And so the gradient actually starts counting at 0. So you're 0G, 1G, 2G, 3G, 4G, 5G, okay? And so visually what you see is that, the arithmetic gradient doesn't actually show any cash flow until that second year, okay? Or second time period. But then what if you have a situation like this, okay? All right, so what if you have a situation like this, where you have a recurring cash flow that starts on time period 1, but then is increasing from there, right? So let's say on time period 1, we have, let's say a cash flow of $100, and time period 2, 200, 300, 400, 500, 600, okay? And so if the standard form for G doesn't start showing up until time period 2, how can we characterize this then, right? Because you can see from this diagram here that the increase is about 100, right? And so just based on the time period to time period increases, this tells us that G should be 100, okay? Right. But then, if we look at this, right? So we start with $100 on year 1, and then we go to $200 on year 2, right? This kind of seems to violate our standard form for G, okay? So if you have a situation like this, and this is very common, you're going to see this a lot. So that's why I'm kind of bringing your attention to it now. You can actually split this up into 2 different types of cash flows, and then just kind of add them together. Okay? So let me kind of show you what that looks like. And so on the one hand here, 2, 3, 6. Okay. On the one hand, we can have our G in standard form, so we'll call this the standard G part. Okay. So it'll be like this, where this is 100, 200, 300, 400, 500. Okay. So for a simple G is equal to 100, this is what our cash flow diagram would look like, right? We'd have 100 starting in time period 2, and then we increase by 100 from each period after that. Okay. So that's one part of this cash flow diagram. But if you compare this, what we have right here, to the starting one, everything is off by 100, right? So everything is $100 less than what it is from the standard. And so the other part that we're splitting here is a uniform series. Maybe I should have used something other than 100, because now we're gonna have G is equal to 100 and A is equal to 100. So maybe I should have done something different. But in this case, they both happen to be the same, but that's not necessarily the case all the time. All right, and so if we add a uniform series with a value of 100 to it, and we can do this because they're both recurring type cash flows, right? And so they both represent a recurring cash flow, and they're both assuming to occur at the same times, right? And so if we add these two together, we add a G of 100 and an A of 100, then that's what gives us this this cash flow diagram up here. Okay. And so when you're looking at arithmetic gradients, you have to be really careful, because a lot of times what you see either visually from a cash flow diagram or what's described to you in a problem is usually a combination of a arithmetic gradient and a uniform series, because the uniform series kind of sets that baseline, and the G only describes to you how much the increases are going to be. Okay. So this right here is the baseline. These are the increases. Right. So definitely be careful about that. When you're doing these problems, because it's very easy to get confused with the arithmetic gradients. Okay. And these are situations where you're going to really want to draw it out too, just so that you can kind of very visually see where the increases are and what the baseline value is. Okay. All right. Any questions on this before we do an example? Okay. All right. So let's do an example. Okay, so in this example, let's say that a friend of yours just bought a new car, okay? And the car is expected to have a certain maintenance schedule over the next 5 years. Okay. And this schedule basically dictates that the maintenance costs are going to go up year by year. And so here is the schedule, and I'm just going to write in table form. All right, so it's a 5-year plan. And so in year one, the maintenance cost is going to be $120. Okay. Year two, it's going to be 150. Year three, it's going to be 180, then 210, and then 240. Okay. All right. So this is good. But your friend is a forward thinker, and so what your friend is saying is that knowing that this is what the costs are going to be, he wants to set aside the money now to cover all the maintenance costs in the future. Okay? All right. And so if we let's assume we have an interest rate of 5%. Okay, so we're going to assume I is equal to 5%. How much money should you set aside right now to cover all of the maintenance costs over the 5 years? Okay. All right. So that's the problem that we're looking at. Okay. Okay. So based on this problem, we're looking for an amount of money that we need to set aside right now, right? So anytime you see now or anything like that, this tells us that we're going to be looking to compute P. Okay. And so that tells us that all the other cash flows in the problem, we're going to convert those to P. Okay. All right. So here we have our cash flow schedule here. Okay. It's in tabular form. And you can see that the maintenance costs starting out are going to be $120.
Okay, and in year one, and they're going to increase by $30 after that. So what we have here is an exact situation of kind of what we described just now, right? We have a baseline cost that's going to start in year one, and then we have the increases. Okay, and so we can split this up into an arithmetic gradient and a uniform series. Okay. All right. So let's start with the baseline value. Let's start with the uniform series. And so the uniform series is usually how much cash flow that's going to happen in the first time period. Okay. And so we have a uniform series value of 120. Okay. And then in this case, the increases, which is the year-to-year increases, are 30. Okay. We have an A of 120 and a G of 30. Okay. And we want to convert both of these to P. And so we're going to use our cash conversion formulas in order to do that. Okay. Okay. So let's go ahead and set that in motion. Okay. All right. So we're going to need two formulas here. So we need to convert first a G into a P. Okay. So let's do that first. So we're going to use our G to P formula. So we have P is equal to G. Right, so this is one of the formulas that we wrote at the beginning of class today. So you have P is equal to G multiplied by quantity 1 plus I raised to the N minus IN minus 1. Okay. All divided by I squared 1 plus I to the N. Okay. All right, so we can go ahead and plug everything into this formula here. We have everything that we need. The interest rate is 0.05. The number of time periods here is 5. And we know G is equal to 30. Okay. We plug all that in. And we get a P value of $247. Okay. And then we're going to convert the uniform series to a P as well. So we're going to use our A to P formula. So P is equal to A times quantity 1 plus I to the N minus 1 divided by I 1 plus I to the N. Okay. So once again, we have everything that we need. And so we plug in for A is 120. We plug in for our interest rate. We plug in for the number of time periods N. And what we get is $520. Okay. All right. So now that we've converted both of these to P, right? So now both of these are the same type of cash flow, right? They're a single lump sum in the present day. We can now add these together. Okay. And so we have 247 plus 520. And what we get from that is $767. All right. Any questions on that example there? All right, so when you're dealing with gradients, a lot of times you're going to have a uniform series in there as well. So make sure you kind of deal with those. Separately. Okay. All right. All right, so we're just about done with the first set of lecture notes. The last thing I want to cover here is something called the compound interest tables. Okay. So the idea with the compound interest tables are to kind of simplify your calculations and make these problems easier to perform. Okay. All right, so what do I mean by that? And so, whenever you're doing these kind of economic analysis type of problems, you're going to end up converting between different types of cash flow a lot. Okay. We've only kind of really scratched the surface. We've only kind of done just the basic calculation. But once we kind of get into more complex problems, especially when we throw things like taxes and inflation into the mix, it's going to be a lot. Okay. And so far, what we've covered, the only way that we've covered so far to convert these cash flows is to use formulas. Which are totally fine. Formulas are great. And in fact, there are some situations where you can only use formulas. Okay. But when you're doing these calculations and you have to do them maybe like a dozen times for a single problem, punching numbers into a formula a dozen times can be a little bit cumbersome. Okay. And kind of the more, generally speaking, the more manual calculations that you're required to do, the more likely it is that you're probably going to make a mistake at some point. Okay, that's just human nature. Okay. So people have realized this, and they've kind of realized the nature of these problems. And so they've developed another way to do these calculations. Okay? And so the compound interest tables are a tabulated list of values for converting between different cash flow types. Okay. And so the whole point of the tables is just to make these faster. Okay. All right. So I'll go over the format for the table first, and I'll kind of show you what the table actually looks like. Because if you're just looking at the table just fresh, it can be a little bit overwhelming because it's a lot of numbers. Okay. But the idea is this, and so notice how the name for this is compound interest tables, plural. Okay. And so the way that these work is that there is a different table for every interest rate. Okay. Okay. And so what you'll see is that we're going to look at the actual tables in a second, but the actual tables is actually it's actually a 23 or 27 page PDF, and each page of that PDF is a different interest rate. Okay, so for example, let's say that we look at the table where I is equal to 4%. Okay, and so the way to use these tables is that for any given problem, usually for a given problem, your interest rate is going to be fixed, and so you can just go to that table in the interest rate in the compound interest tables. Okay. And then the tables themselves look like this. And so there's one column. The first column is going to be N. Okay. And so that N is the same N that we've been using in our formulas. Okay. And then from here, there are different columns with different, they look like ratios. Okay. So for example, the first column will be F over P. Okay. Next column will be P over F. Next will be A over F. and A over P, F over A, P over A over G, and P over G. Okay. All right, so it's a lot of data, and if you kind of don't really know what you're looking for, it can be hard to kind of find what you need. Okay. All right, so the way to read these tables is, first of all, you're going to find the table for the interest rate that you're looking at. Okay. And then each of the rows are going to be labeled by different n values. Okay. Okay, so for the first 6 rows, row 1 is going to be n is equal to 1, 2, 3, 4, 5, and so on. Okay. Okay. And then what you're going to see in these columns here is that there's going to be a value. Okay. And that value is going to be your conversion value. So for instance, this would be like 1.04. This might be some other decimal, 0.9 something. Okay. Okay. You're just going to see a bunch of decimal values inside this table. Okay. All right. So the way to use these tables is that, those values in the columns there, those are your conversion factors. Okay. And which conversion factors are they? Well, it tells you at the top of the column. Okay. And so if you look at kind of what's given to you in the top of the column, you see that it's a ratio of 2 different types of cash flows, right? So that first column there is F over P. Okay? And so what this is telling you that this column here is if you want to convert a present sum P to an F. Okay. And so the way to use it would be like this. So let's say that we have a present sum of, let's say $200. Okay. And we want to convert it to an F. Okay. At a 4% interest rate, and n is equal to 1. Okay. So normally for this, we would use our compound interest formula. Okay, so F over P, or F is equal to P times 1 plus I the n power. Okay. So you plug in I is equal to 0.04, n is equal to 1. Okay. That's one way to do it. Okay. The other way to do it is to look at the table, right? And so if you're going to convert a P to an F, okay, you can just multiply by whatever is in this table, okay? And so you would say F is equal to P multiplied by 1.04. Okay? And if your P here is 200, you do 200 times 1.04, and you get 208. And if you'll notice, the values that you have in the columns are exactly, all the terms that we compute in the formulas for a certain value of I and a certain value of N. Okay. So all these tables do is they basically just fast track those formulas for you. Okay. So for this example here, this is a pretty simple example. It'd probably honestly be faster if you to use the formula. But if you're doing a more complicated conversion involving like a uniform series or maybe an arithmetic gradient, okay, using the compound interest table here will save you a lot of time. Okay. And what you'll see, for all the future examples I'm going to do, I'm for the most part, I'm going to be assuming the tables, just to go a little bit fast. Okay. But of course, you can do all these problems with the formulas. It's just that sometimes it's faster to use the tables themselves. Okay. All right. Any questions on this? I do have an example for this to kind of show you. Okay. All right. So let's do one quick example here to kind of show you how it's actually used. Okay. And I have the PDF pulled up on the computer here, so I'll kind of show you. I'll show you that. Okay. So let's do a fairly simple example. So let's say that we want to invest $1,500 today. Okay. And let's say that you're going to store it in a savings account with a 6% APY. APY is just another term for interest. Okay. Right. Okay. And so what we want to find out is what is the equivalent future worth in 5 years. Okay. And so, this problem right here, we can easily do with the formulas, but let's see how to use it. Let's see how to use it during the tables. Okay. So in this problem, we want to find a future worth, and so that means we're going to solve for F. Okay. And what we're given is a P, right? Because we're given that we have $1,500 today. Okay? So our F here is going to be 1,500. Okay. Normally we would plug in the formula here, but let's see how to do it with the table. Okay? So this is the format that I'm typically going to use for the compound interest tables. Okay. And so what you're going to see me do is that I'm going to multiply whatever cash flow we have by a conversion factor, right? And I'm going to put that conversion factor in parentheses. Okay. I mixed up the interest rate. So the interest rate is 6% and the end is 5 years. Sorry about that. Okay. All right. So what I have here in this set of parentheses, that this is our conversion factor. Okay. And this is a conversion factor that we're going to look up in the tables. Okay. And I'll show you how to do that in a second. Okay. But to read this conversion factor, okay, you notice that there's 3 components to this. So the first is going to be a ratio of some kind. Okay. And so this first one is going to be the type of conversion. Okay. And so in this case, we're transforming from a present sum to a future sum. And so the type of conversion that we need is an F over P. Okay. The next entry we have here is, of course, the interest rate. Okay. And then the last entry here is the N, or the number of time periods. Okay. All right. And so from all this information, we can see that we need the type of conversion. We're going to look at the compound interest tables for 6%, and we're going to go to the 5th row of that table. Okay. All right, and then what you'll see here is that there is going to be an entry in the table that belongs to this this combination exactly. Okay. Any questions on this before we jump to the compound interest tables? Okay. All right, so let me go ahead and switch over to the computer screen. Okay, so what I have here is the compound interest tables, and so this is available on the Canvas site, and so it's actually on the homepage. You can download this. Okay, so it is a 32-page PDF. Oh, it's bigger than I thought. Okay, and so as you kind of scroll down here, you can see that each page here is an interest rate, has a different interest rate. Okay. So the interest rate is in the top of the table right here. Okay. And so this first table here is for an interest rate of 0.25 or 1/4. Okay. This next table here is for an interest rate of 0.5%. Next is 3/4, then 1%, then 1 1/4%, 1 1/2, okay, 1 3/4, 2%. Okay. So the first few tables are the interest rate only grows up by a certain amount. but as you kind of get further down, the increases start to get higher. Okay, so we're going to keep scrolling down because if you look at the problem that we have an interest rate of 6%. And so we need to go to the table that has interest rate of 6% here. Okay, so keep scrolling, 4%, 4.5%, 5%, 6% right here. Okay. All right, so we're in the compound interest table for 6% here. Okay. So that's good. So now we need to make use of the other pieces of information that we're given. Okay. The first thing is that we know the type of conversion that we're going to use is an F over P. Okay. And so we're going to go to the F over P column. And so we know that we're going to be in this column right here. Okay. And then the row is determined by our N value. Okay. So our N value is 5, right? So we go to the 5th row. And so you can see our conversion factor in this case is 1.338. Okay. And so in order to convert between a present sum and a future sum for an interest rate of 6% and the number of time periods of 5, we just have to multiply by 1.33. Okay. All right. So let's go ahead and do that. So let's remember that number 1.338, and let's go ahead and bring that to our notes. Okay. Okay. Let me rewrite it down here just to make it a bit more easier to see. Okay. So ultimately, we want to compute this future sum, right? And so we're given that P is equal to 1,500. And what we just looked up from the tables is that this conversion factor is 1.338. Okay. All right. And so from here, now that we've looked up this this value in the table, so this is from the tables. Let me just point this right here. Okay. All we have to do now is just multiply these two numbers. Okay. So we have F is equal to 1,500 times 1.338. We perform that multiplication. We get 2007. All right. And so for situations like this, and especially for situations where you have to do non-standard type of conversions, the compound interest tables can save you a lot of time. Okay. So for the purposes of this class, I don't really have a preference on what you use for your assignments. So you can use the formulas if you prefer. You can use the compound interest tables if you prefer. It doesn't really matter to me. And so, whichever you find easier, whichever you find more intuitive, you can use it. Okay. One limitation that I do want to make you aware of, though, is that the compound interest tables only really work when you have a table of that specific interest rate. Okay. And so for this past problem, usually integer values are pretty safe. And so if your interest rate is some integer value, 4, 5, 6, 7, 8, 9, 10, you're pretty good. Okay. As you saw from the tables, there are some decimal values. And so if you're on the lower end, like 2.5, 1.25 interest rate is there. Okay. But this is not going to work for every interest rate. So let's say that you have a problem with an interest rate of, I'll do one that's definitely not in the table. So let's do 6.25%. Okay. So there's no compound interest table for this. Okay. You can try to play the game where you try to kind of interpolate between the different tables, but you're not going to end up with an accurate result because these formulas depend on a lot of exponentials. Okay. And so if you're given an interest rate that you don't have a table for, this is something that you need to use the formulas for. Okay. That's the only limitation that that you have there. Okay. But if you have a problem with an interest rate that you have a table for, go ahead and use the tables, and I promise you it'll save you some time relative to using the formulas. Okay. But you know, don't try to fit a round peg into a square hole, right? So don't try to use the tables for an interest rate that you don't have. Okay. You're going to end up with the wrong answer. Okay. Any questions on any of this? All right, so you'll see me start using the tables, especially over the next few weeks as we start to do I call them kind of like real problems, right? And so you'll get plenty of practice using the tables, and of course you can use them on your homework assignments too. So if you haven't gone to the very last problem on homework 1, this is a situation where procrastinating does actually help you out a little bit because you can actually use, I think you can use the compound interest tables for a couple of them. But I think for some of them, I give you a decimal interest rates that you can't. So feel free to use the tables. Okay. All right. And so that kind of wraps up our first kind of big unit in terms of cash flow, equivalents, interest rates, compound interest tables. Okay. So everything that we've learned in this unit is kind of sets the foundation. They're kind of like our building blocks. And from here, we're going to do more and more complicated stuff, more kind of real stuff. All right. Question. So I got stuck on the last 2 problems of homework and I couldn't understand why until now. Oh, yeah. Yeah. So yeah, if the compound interest tables work, I think there's some gradients that are in the last 2 problems as well. So you may have to use the gradient formulas for that as well. Yeah. Mm-hmm. Okay. All right. So let's go ahead and move on to the next topic. So we're kind of moving on here. Okay. And so our next big topic that we're going to be talking about is something called present worth analysis. All right. So present worth analysis is the first of 3 different techniques that we're going to be learning for performing economic analysis. Okay. And so even though these 3 techniques are different, they all kind of seek to accomplish the same goal. Okay. And so they're all used for kind of the same situation that you come across pretty often in engineering and even in your daily life as well. Okay. And so present worth analysis is a way to perform what I call an economic comparison. Okay. All right. So what do I mean? What do I mean by that? What do I mean by economic comparison? So a lot of times, in your engineering life and in your daily life, you have the option of investing or buying 2 different types of options or alternatives. Okay. So let's say that we have alternative A versus alternative B. Okay. Right. And you're trying to decide which one that you should buy. Okay. And so for an example, let's say that you're working on a construction project for work, and you have the option of going with vendor A or vendor B for purchasing a piece of equipment. Okay, whether it be a pump or whether it be like a crane, a truck, or something like that. Okay, and you're trying to decide which one it's going to be. Okay, and so obviously, you want to pick the one that's going to be a better option. For a lot of different reasons. But for this case, we're going to focus on the economics. Okay. So which Okay. And so what do I mean by a better economic option? Well, the better economic option is going to be the one with the lower overall cost. Or maybe you're looking at the one, maybe you're also looking at revenues at the same time too, right? And so maybe you're looking at the alternative that's going to have a better or higher overall benefit. Okay. Or maybe if you're considering both costs and benefits for your project, you're gonna pick the one that has the highest or most positive overall cash flow. So you want to pick the one that does all these things. Okay. And so at first glance, this may seem like an easy something easy to do, right? And so you just pick the one that costs the lowest, or the one that kind of makes you the most money. And if you do basic, the assumption is that if you can do basic arithmetic, you can pick these two. Okay. But um, what we've seen so far, in everything that we've covered in this class, is that this question is not as simple or not as straightforward as it sounds, because of the concept of time. And so because the value of money changes with time, and the fact that we have interest rates, okay. And what you'll see is that some alternatives, may have kind of non-standard cash flows, or comparing one to the other may not be as super straightforward as you think. Okay. We need a way to kind of perform this analysis, or to perform this comparison in kind of a very systematic way. Okay. And that's where a lot of the tools, a lot of the techniques that we just learned kind of come into play. Okay. And so that's kind of where we're at, which is present worth analysis. So essentially what present worth analysis is that, we're going to use the formulas, we're going to use the tables, we're going to use the concept of equivalence. We're going to use all those things to perform these economic comparisons in a systematic, kind of consistent way. Okay. And the idea of present worth analysis is actually quite simple. Especially, that we've taken all this time to talk about, um, interest rates and equivalents and all that. Okay. So the idea with present worth analysis is to take all the cash flows for each option or each alternative and convert them to a present sum. Okay. So we want to compute. So we're going to compute an equivalent present sum for each of the alternatives, and we're going to compare them directly with one another. Okay. Generally speaking, whichever one has the most positive present sum, that's going to be the best economic alternative. Right, and so that's it. And so, all the problems that we've been doing, we're just doing them again. It's just that you're doing more than one per problem. And you're going to pick the one with the most positive present. Okay. All right. So, we've spent kind of the last couple of weeks I've been going kind of a little bit slower than usual, kind of building up these ideas of equivalence, standard forms, cash flow conversions. So now we're just kind of basically just applying it to these types of problems here. Any questions on this so far? Okay. All right. So, but before we start doing some examples, let's talk about some assumptions that we're going to make. Because these are kind of important to state, and so these are assumptions, and so we're not going to state these for every single problem, but they're going to be implied. Okay. Some of these, we don't really know how to deal with yet, just because we haven't gone to taxes yet or inflation. Essentially, we're going to ignore all that stuff. Okay. All right. The number one assumption, though, probably the one that's going to be the most simplifying, is that when we're doing these types of problems, we're going to assume that each option or each alternative will perform the same. Okay. And so when we're considering between, three different vendors, in reality, of course, there's difference in performance, there's difference in quality. All that stuff needs to be taken into account. But for now, we're just going to keep things simple, and we're going to assume that all options will perform the same if we were to go with that option. So we can kind of take that out of the equation for them. Okay. Even though in reality, this is a very real issue that you have to deal with, is different qualities between different vendors and different companies and such and such. Okay. Okay. Number two, we're going to ignore taxes. Okay. We'll see later on in about maybe 3 or 4 weeks that taxes do actually make a pretty big impact in terms of how we're going to go with certain options. Okay. Especially when you start talking about tax write-offs and all that stuff, right? We'll go through all that in detail, but for now, we're going to keep things simple, and we're going to ignore taxes. Okay. Okay. And we're also going to ignore any effects of inflation. Okay. And so whenever you're planning for a project that's going to take place over a long period of time, okay, especially when you're accounting for recurring costs, things like maintenance costs, things like paying employees, things like that, all of those things are going to go up because of inflation. And normally you would have to account for them, but for now we're just going to ignore that and kind of keep things simple. Okay. Okay, so if we have a recurring cost, it's just going to recur at that same value, unless we have an arithmetic gradient that's kind of built into it. Okay. Okay. All right, so that's enough talking about it. Let's get into a problem. Okay. So let's say that you're working at an engineering firm and your company is deciding between the purchase of two different types of machines, okay, for performing the same job. Okay. Both of these machines will have a useful life of 5 years, and so they're expected to last the same amount of time. I guess I should say, your company has narrowed it down to two different vendors, okay? And so both of the vendors that they're considering have a useful life of 5 years. And we're going to assume just for now that each of these machines are going to have no salvage value, okay? And so your company is not expected to sell this machine afterwards. You're just going to trash it, basically. Okay. And so we're going to give it the very creative name of machine A and machine B, okay? So let's say machine A has an upfront cost of $10,000. And based on its performance or based on what it can do, it's going to save the company $3,000 per year. Whereas machine B, okay, machine B has an upfront cost of 13,500. So a bit of a higher upfront cost. Okay. Machine B will provide the company $3,000 in cost savings in the first year. Okay. And so for the first year, both machine A and machine B are equivalent. Okay. But based on the increased capacity of machine B, okay, the cost savings is going to increase year to year. Yeah. Oh yeah. Come on, iPad. The rain must be getting to the. There we go. Okay. And so if you map this out, that means the cost savings in year 2 will be 3,500. $4,000 in year 3. All right. So your company's trying to decide, should it buy machine A or machine B? Okay. And so if we assume an interest rate of 7%, okay. Let's do the following for this problem. Okay. Number one, for each option, let's draw their cash flow diagram. So part one here is just drawing their cash flow diagrams. And number two, let's do present worth analysis. Okay. So we're going to use present worth analysis to decide which machine your company should buy. All right. So there's a lot of text in this one. I went ahead and kind of wrote basically all the text for this problem, just because, again, like usual, I want to highlight kind of the different parts of this problem so we can talk about it. Okay. Any questions on just the problem statement for this example here? Okay. All right. So let's go ahead and start working on these problems here. Okay. So let's start with the cash flow diagram. So these are pretty simple. All right. So before we draw the cash flow diagram, one small note about kind of the verbiage of this problem. Okay. And so the way that this problem kind of states its cash flows, or at least for the cost savings, right, is that these machines will save the company a certain amount each year. Okay. Whenever you see this type of verbiage in the problem, okay, saving money is like the same thing as making money, right? And so like the saying goes, right? A penny saved is a penny earned, right? And so we're going to go by that same kind of logic here. So whenever you see a problem that says that this machine or this project is going to save money, right? We're to consider that as a positive cash flow. We're going to consider that as a revenue. Okay. Okay. So with that in mind, let's go ahead and draw the cash flow diagrams. Okay, so let's go machine A. Right, so we have a 5-year time horizon. Okay. So machine A has an initial cost of $10,000. Okay, so that's how much we pay up front. We have 10,000. Just like that. Okay. And then machine A is going to save us a flat amount of 3,000 per year. Okay, so we got 3,000, 3,000, 3,000, 3,000, 3,000. Okay. Okay. So pretty straightforward. So for machine A, we only have two cash flows to consider. We have the initial cost, and we have a uniform series that shows its revenue. Okay. All right. So let's look at machine B. All right. So machine B had a higher initial cost. So machine B had an initial cost of 13,500. But compared to machine B has an increased cost savings each year. Okay? And that increase is going to go $500 per year. So we're going to start at 3,000. then 3,500, 4,000, 4,500, and then $5,000 of cost savings at the end of year 5. Okay. Okay, so those are our cash flow diagrams. So pretty straightforward in this case. And so, we can see from the cash flow diagrams that machine A has a present value of minus $10,000. Okay. We'll call that P1. Okay. You also have an A positive 3,000. Okay. For machine B, we have a present initial cost of minus 13,500. Okay. We have an A value here, the same. So remember, we have the same pattern here of a recurring cash flow that increases, right? So we have to specify its baseline value of 3,000. Okay. And then we have a G value of 500 because that's how much it's increasing. Okay. Okay, so let's use this information and let's convert for each machine. Let's convert all those cash flows to a present worth. Okay. Okay. So we're going to compute a present worth of machine A and a present worth of machine B. Okay. All right. And so we're in luck because some of these cash flows are already in present form. And so for those ones, we don't need to do any conversions. Okay. So let's look at machine A first. And so we have an initial cost of minus 10,000. Okay. Right. So that minus 10,000 from machine A is already in present form, right? That's an amount of money that we have to pay today to own that machine. Okay. So that minus 10,000, we don't have to do any conversion. So we kind of leave it alone. It's already P, no conversion. Okay. And notice how I put a negative because that 10,000 is an initial cost, right? So costs are typically negative. Okay. Then we have our $3,000 uniform series. Okay. So we need to convert this $3,000 to a present sum. So let's use our compound interest table. All right, so the conversion factor that we're looking for here is P over A, right? Because we have an A that we need to convert to a P. Okay. So I have 3,000 P over A. The interest rate in this case is 7%. And the number of time periods here is 5. Okay. All right, so this factor here we can look up in the table. Which we will do in a second. Okay. But let's write out the expression for present worth of B. Okay. So when you're doing these types of problems, it's tempting when you're writing out these expressions to look up these conversion factors from the table kind of as you're doing it. But one useful technique that ends up saving you some time is that a lot of times these conversion factors are used in multiple times in the same problem. Okay? And so, usually it's good to kind of write out all the factors that you need and then just look at the table once. Okay? All right, so let's write out the expression for present worth of B. So we have our initial cost, which is minus 13,500. Okay. Just so I can A, that minus 13,500 is already in present form. So there's nothing, we don't need to convert that. Okay. Okay. Next, we have our uniform series of 3,000. So that's going to be 3,000 times P over A, 7% and 5. Okay. So you can see that's the exact same factor that we're going to need in present worth of A. So, we can kind of save ourselves some time, put it once. Okay. And then we have our G, which is 500. And so to convert that to a present sum, we need a P over G factor, 7%. and 5. Okay. All right. All right, so unfortunately, we are out of time, and so, I'm gonna leave you on a cliffhanger, unfortunately. Because switching to the computer here to look up the table is gonna take a bit of time. So we'll pick up with this first thing on Thursday, so we'll see the conclusion of this problem. I think it'll be a good refresher on how to use the table as well, so I think that'll be kind of a good place to start from, okay? And so when we come back on Thursday, we'll finish up this example. We'll do more examples of present worth analysis. And we'll throw in some additional wrinkles in there as well. Okay. All right. Any final questions before we wrap it up for today? Okay. All right. So thank you guys for coming today. Stay dry, stay safe out there. It is still raining very hard. So take care of yourselves, and I will see you guys on Thursday. Thanks, guys. You guys stay safe out there. Thank you.